Okay, good morning. We'll see next topic, that is response of damped system under rotating unbalance. Okay, so we'll see unbalance in rotating machine is one of the main cause of vibration. Okay, if there is a unbalance of mass, okay, one side mass is more, another side mass is less. Okay, so that is called unbalancing. Or if the rotation of any disc or any rotating member happening where its axis is offset to the rotational axis. Okay, if it is rotational axis of a member is offset to the center of rotation, then there will be an unbalance. Okay, so such in cases we can see in machineries where worn outs are there, or some defects are in the manufacturing process. Okay, where the offset has been taken place, or due to worn out, see, mass of the system going to changes. Okay, that time the vibration going to arises. Okay, such vibration is called rotating unbalanced vibration. Okay, so it is undesirable. Okay, now we will study how to we will study the that scenario, how it is going to happen. Okay, we'll see here one mass is there. Okay, two rotational bodies are there. Okay, so here there is an eccentricity. Okay, so from this point to this point. Okay, so there is a eccentricity, offset is there, here also same. Okay, due to this eccentricity there is a imbalance in the system. Okay, so it is going to violate. Okay, or it is going to vibrate. Okay, now how to study this? Okay, what is the forces are exerting on this? You see here, the total force is mass, okay, the amount of eccentricity into how much frequency it is rotating, angular frequency it is rotating. So that is the total mass of the force exerted due to unbalance. Okay, so if it is E is not there, okay, it will be direct m into omega square. Okay, but here there is a eccentricity, so you have to consider that alternative picture. Okay, m by 2y, it is because there is a one half mass. Okay, there is another half mass. Okay, so if you take in component, so one will become cos component, another will become sin component. Okay, so hope you understood this, how it came. Okay, suppose if eccentricity is not there, the force exerted will be m omega square. It is almost like mx double dot. Okay, that is force into acceleration. Okay, here omega square is there, so the frequency is there, m omega square. Okay, now we'll see what is it. The total mass of the machine is m, and there are two eccentric masses, that is m1 and m2. Okay, in opposite direction with a constant angular velocity omega. So they are, one is rotating this way, another is rotating this way. Okay, the total vertical component excitation is always given by ft me omega square into sin omega t. Okay, the vertical component. Okay, this is horizontal component, this is vertical component. Okay, the vertical component is sin omega t. Okay, the magnitude is me omega square. Okay, if eccentricity is not there, so it will be m omega square. Okay, let's see what is eccentricity. It is a offset, okay, from the center point. Okay, the equation of motion can be written as this remains same, spring is there, damper is there, mass is there. Okay, so mx double dot cx dot plus kx. Only variation here is due to force. Okay, the force is varying because of eccentricity. Okay, there is a disturbance. Okay, that's why it is wobbling. Okay, wobbling motion. Okay, due to that there is a force exerting. Okay, what is that force? So we are going to consider it here. Okay, rest other things remain same. Okay, so whatever the derivation we did in the previous applicable to this, only thing is here we have different force. Okay, forcing function is different, that is ft me omega square sin omega t. Okay, next, the solution of this equation will be identical to equation. Okay, last equation, if we replace m by f naught and m by m and f naught by m and me omega square respectively. Okay, if we replace m with m, total mass m, okay, f naught with respect to me omega square respectively. Okay, if we replace m with m and f naught by me omega square, the solution can be expressed as like this. Okay, xp is equal to s sin omega t minus pi. Okay, this is our particular solution last we did. Okay, the solution to this is x. Okay, f naught, what is f naught? Instead of f naught we are writing mu omega square. Okay, instead of small m we are writing big M. Okay, the total mass. Okay, so you will get equation same as our first derivation. Okay, root of k minus m omega whole square into whole square plus c omega whole square. Okay, if we simplify it we will get pi. Pi is tan is cw by this term. Okay, so we will get phase angle. Okay, so this is our rotating unbalanced. Okay, rest everything will be same. Okay, since we are not deriving it, we are directly comparing with the first derivation and we are replacing here. Okay, we know that, right? X is equal to f naught divided by root of k minus m omega square whole square plus c omega whole square into. Okay, so here replace m with m omega square. Why you want to replace? Because the magnitude of force due to unbalancing is m omega square. Okay, now m with total mass m. Okay, so this becomes the formula. Okay, now we will solve one small problem on this. Okay, the first problem. The problem is schematic diagram of Francis water turbine. Okay, this is a Francis water diagram where the flow is axial. Okay, so the rotation is in this axis and the flow is also in this axis. Okay, now the flow from point A into the blades B. Okay, down into the tail race. Okay, from here it is flowing and it is going down. The rotor has a mass of 250 kg. Okay, this rotor has a mass of 250 kg. This is okay. An unbalanced mass me is 5 kg/mm. Okay, there is an unbalanced. Okay, so there is a unbalanced mass that is 5 kg/mm. Okay, due to some manufacturing process or some other defects, there is a unbalanced. Okay, that unbalanced quantity is 5 kg/mm. The radial clearance between the rotor and the stator is 5 mm. Okay, here radial distance is 5 mm. The turbine operates in the speed range of 600 to 6000 rpm. Okay, this is the range. The steel shaft carrying the rotor can be assumed to be clamped to the bearing. Okay, this shaft. Okay, this shaft is assumed to be clamped to the bearings. Okay, determine the diameter of the shaft so that the rotor is always clear of the stator at all the operating speeds of the turbine. Assume the damping to be negligible. Okay, assuming that it is a undamped system. Okay, there is no C is not there, damping constant is not there, only it is a undamped system. We have to find out the diameter of the shaft. Okay, based on this. Okay, considering unbalance, considering the vibrating system, so you have to find out what is the required diameter for the shaft. Okay, to operate with the all range of their speeds. Okay, between 600 to 6000. Okay, now we'll see how to solve. Write down what is the given. First given is mass, that is big M, mass of the turbine blade. Okay, so that is 250 kg. Okay, next me unbalance is 5 kg/mm, so it is 5 into 10 raised to minus 3 kg meter. Okay, x, the offset displacement is 5, that is 5 into 10 raised to minus 3. Okay, the speed of the turbine is from 600 to 6000 rpm and there is no damping, that's why C is 0. Okay, now let omega minimum. Okay, so 600 is the speed of rotation, 600 is the maximum. Okay, so you have to find out what is the frequency. Okay, omega mean is 2 pi divided by 60 into 600, so it is 62.83. okay, maximum frequency is 2 pi by 60 into 6000, that is 620.532 rad per second. Okay, now you have to find out these two. Okay, minimum, omega minimum and omega maximum. Okay, now we'll see next the x. So what is the formula? X is equal to me omega square k minus m omega square whole square c into m omega square into half. Okay, now you substitute values. Okay, by putting c is equal to 0, since it is a undamped system, c will be 0. Okay, put c is equal to 0. So what is the formula? me omega square remains same, this term remains same. Okay, if I simplify this, I will get mu omega square k 1, it will come this side, k mu omega square divided by k. Okay, this k will send this side. Okay, now m by k is omega n square. Okay, mu omega square remains same, k is taken outside. Okay, 1 minus m omega square km. Okay, k by m is omega n square, this term. Now if I simplify, mu omega square is equal to k into 1 minus r square. Okay, now we will find out what is natural frequency. The natural frequency is omega n, that is root k by m. Okay, k is unknown. Okay, 250. Okay, mass is 250. So you will get 0.063245 root of k rads. Okay, next, if k is in Newton meter, for omega is equal to 2 pi rad. Okay, 2 pi rad. Okay, 2 pi rad means this, where we find out this is 2 pi rad. Okay, 20 pi, that is how it is 25, 60, 60, 10. Okay, so you'll get 2 pi. This will be 200 pi. Okay, next, for 2 pi rad, okay, how much k we are going to get? Okay, put x mu omega square 1 k into 1 minus m omega square omega n whole square. Okay, omega n whole square is this. Okay, omega is 20 pi. Okay, put x is equal to 0.005, where it is this gap, x is 0.005, this gap. Okay, 0.005 meter it is. Okay, there it is mm, so you convert it into meter. Okay, meter you put 0.005, m is this eccentricity. Okay, eccentricity unbalance, that is me. Me is 0.5 into 10 raised to minus 3. Okay, you should not get confused. Okay, mass and this mass is different. Don't put m is equal to 50 here. Okay, this total term me combined, you will get 5 into 10 raised to minus 3. This is given unbalanced. Okay, next, omega square is 2 pi, 20 pi. Okay, put 20 pi here, this value 0.004 into k. How it came? Omega n value. Okay, here if you square it, you will get this. Okay, now you check. Okay, if you square it, you will get some 0.999 something, so 0.04 you have taken k. Okay, now you simplify for k, everything is there, simplify for k. Okay, now if you simplify for k, let's see, simplify for k, so you will get this. Okay, k is equal to 10 into 10 raised to minus 10 raised to 4 pi square Newton meter. Okay, you can keep it in numerical instead of pi. If you don't want to keep in terms of pi, then you can keep it in terms of pi square. Okay, next, this is one stiffness. Okay, now you have another condition where it is rotating at 6000 rpm. Okay, that time the frequency is 200 pi. Okay, here we are solved. Okay, not kept in pi, instead of that we are kept in numerical value. Okay, out 200 pi 60, 60, so it is 100, 2 into 100, 200. Okay, that's simple. If you don't want to keep, you can keep it in pi, or you can keep it in value 628 Newton per rad per second. Okay, now here instead of 200 you put, instead of 20 you put 200. Okay, same formula, you have to put, instead of 200, instead of 20 you put 200. Okay, so here only changed, rest everything will be remain same. Okay, now find value of k. K value is 10.04 into 10 raised to 6 pi square. Okay, here 10 raised to 4, here it is 10 raised to 6. Okay, this is the stiffness of the system. Okay, from stiffness, if you know stiffness, you can find out what is the diameter. How to find a diameter? Since the stiffness of the cantilever beam supported a load, okay, a rotor at the end is given by, okay, k is equal to ei by l cube. Okay, this is the formula for cantilever beam stiffness. Okay, K is equal to 3I by L cube. Okay, you should remember this formula. Okay, I is equal to pi due to the power of 4 by 64 moment of inertia. Okay, L cube is length. Okay, 3 E is Young's modulus. Okay, now we'll see the diameter of the beam can be found. Okay, now put here. Okay, d to the power of 4 is there. No? Put d to the power of 4. 64 will go this side. 3I will come this side. Okay, L square will go this side. Okay, 64 K L cube. Okay, 64 K L cube divided by 3 pi E. Okay, 3 pi E. Okay, now 64 into K is, you have taken the least value. Take the least value, don't take the highest value. Okay, take the least value 0.05 into 10 raised to 4 pi square. Okay, next length, that is 2 meter, 2 cube. Okay, this is 0.027 into 10 raised to 11. Okay, this is steel. Okay, if it is not given, take the steel value. Okay, steel value is 207 GPa. Okay, now you substitute and find out. Okay, let me check whether it is given in the data or not. If it is not given, we will give in the exam. Okay, okay, so it is given as the steel. Okay, steel shaft. Okay, the material is given in the question, that is steel. That's why we are going with the 207 GPa. Okay, 207 GPa. Okay, steel Young's modulus. Should remember that. You take around 200 or 210 something. Okay, or you take 207 only. Okay, I think you are done using same thing in design of machine elements. Okay, in 2 also, in 1 also. Okay, now K is the least value, length is given 2. Okay, 2 meter, so it is taken here. Okay, meter cube 64 is here. Okay, 33 pi is here. Okay, now the solution is 2.6005 into 10 raised to minus 4 meter. Okay, so if you take d, okay, 4 times, root 4 times, okay, you will get d is equal to 0.127 meter. Okay, so it is 127 mm. Okay, that is the shaft diameter required. Okay, understood? Okay, you see one by one you will get the problem. What is the problem? Okay, so I will explain once again, simplified. Okay, there is a Francis turbine. Okay, so it is given like this. Okay, where its mass is given. Okay, the stator, this thing is given. Okay, length is given in the figure itself. Okay, it is not given in the problem, so length is given. Okay, now this is blades and it is rotating in range of 600 to 6000. You have to find out the stiffness of this. Okay, so what is the formula we have? This formula we have. Okay, the force and response of this system. Okay, rotating unbalanced system. Since there is unbalance, so you have to take me omega square. Okay, instead of f naught. Okay, now put c is equal to 0 since there is no damping. Okay, once we get this, okay, stiffness we have to find out. Stiffness is not given. Okay, so that is the main agenda here. Once we know stiffness, we can find out deflection. Okay, once we know deflection, we can find out what is the diameter of this. Okay, using deflection of beam problem. Okay, once we know deflection of the beam problem, we can substitute in cantilever's formula, then we can find out what is the diameter required. Okay, that is the overall idea here. Okay, now you should know this formula because you need to find out what is the K value. Okay, omega square we know. Okay, me we know, mass they have, and natural frequency we can find out. Only thing we don't know what is K. Okay, using this, so we can substitute here. Okay, K is here, K is here. Okay, so there are two omegas are there. Okay, omega minimum and omega maximum. Okay, find out two responses. Okay, in terms of K. Okay, once you find out two K's, okay, so whichever the least is there, you consider that for determining the shaft diameter. Okay, so since it is a cantilever beam, we consider cantilever beam. The stiffness of the cantilever beam is given by K is equal to 3A by L cube. Okay, is equal to 3A by L cube. Okay, now put I is equal to pi to the power of 4 by 64. E is Young's modulus of the shaft. Shaft is steel, so they have given steel, but they are not given Young's modulus. You should know that Young's modulus, and you should know this formula. Okay, so find out D. Okay, so this is the overall picture of this problem. Okay, so this may be asked for 10 marks. Okay, so you should be prepared. Okay, this is all our application level problems. Okay, if you have not understood anything, or if you are find any mistakes here, or if you are not able to understand how to convert these things, so you should ping me and ask. Okay, individually. Okay.